So you might not know how big the electron is, but you should know about how big the atom is. And so how big are atoms, roughly? 6.022 times 10 to the 23rd, negative 23rd. 6.022 times 10 to the negative 23rd. What, meters? Meters? Meters or millimeters? Yeah, the reason is chemistry, when we're thinking about structure, composition, and properties, we take a two-pronged approach. There's definitely some memorization involved in chemistry. You can't just derive everything theoretically. For example, what is chlorine? Excuse me. Is chlorine a solid, liquid, or gas? It's a gas. Chlorine's a gas. Now, if somebody asks you, well, prove using theory that chlorine is a gas at room temperature and 1 atmosphere pressure, is that an easy thing to do? To prove it mathematically using theory? No, it's just easier to memorize it or to observe it. And then we look for trends that way. Well, the same thing, we got to memorize some things so that we have a fixed frame of reference. So if you've never thought about the size of the atom, then this could be perfectly fine, maybe. 6.022 times 10 to the minus 23rd. But if you have dealt with atoms, then you'd say, well, that's way too small. It's way too small. It's more like, the size of atoms is more like 1 to 5 angstroms in diameter. Have you heard of an angstrom before? An angstrom is defined as 10 to the minus 10 meters. Well, you know what 10 to the minus 12 meters is. What is 10 to the minus 12? 10 to the minus 12 is called a 10 to the minus 12 using metric prefixes. What is it called? Pico, right? 10 to the minus. And so that's close to pico. 10 to the minus 9 is called a nano. Is that right? Yeah. Micro, nano, pico. And so it would be nano. And so we could do it nano, but we would get decimals. We don't want to do that. And so we're going to go to pico, because in terms of picometers, this would be like 100 to 500 picometers in diameter. This is just rough. There are atoms less than 100, there are atoms greater than 500. They're about that. And so the electrons must be small because the electrons got to fit in there, right? It'll be smaller than that. But we don't talk about the size of an electron. We can talk about the size of an atom, no problem. But how can we talk about the size of an atom? Because does the atom have a hard shell on it? No, atoms don't have a hard shell. The way we talk about atoms is the average radius. It depends on how forcefully you put that probe in there. If you use a little bit more force, you can get in there deeper into the electron cloud, we call it, right? And that means its radius is a little smaller. And then you increase that force, right? There's nothing stopping it. And so what we see is that probe could be other atoms. And so we see how this atom bonds to a whole bunch of other atoms. And then what we do is we get the average. We get the average radius, depending on it. And so for some of these atoms, we have hundreds, hundreds of different radii that will just take the average, and this is the average radius of that particular atom. For others, there aren't that many, It's not that much data. But when we look in a table of radii or diameters, they're all averages of experimental measurements. And so this is, this shell just represents the average diameter of this atom. Of course, the diameter can be smaller if you can squeeze something in there deeper, or bigger if you can't, because you got electrical repulsions resisting. All right, so that's the atom, but as far as the nucleus goes, how big is the nucleus? And so I kind of like the Chem 4 analogy for this, because I think, and you have to correct me if I'm wrong, but I think Chem 4 explains it like this. If a nucleus were do they say, a golf ball? Is that right? If the nucleus were a golf ball, then the atom would be a... If the nucleus were the size of a golf ball, then the atom would be the size of a golf course? That seems about right, but I think they said it would be the size of a football field, so much smaller than the golf course. And so what does that work out to? I did this a long time ago, but you know the numbers vary depending on a lot of factors, but it's about 1/10,000th the size of an atom. And so times the diameter of the atom. This is not the distance in Coulomb's law, it's just the diameter of the atom. And so it's about 10,000 times smaller than the atom itself. In other words, the nucleus is very tiny. And so that means the protons and the neutrons are extremely tiny to fit into that nucleus. If somebody asks you, what is the, how big is a proton? Is that something that can't be answered, or is that something that can be? Because if somebody asks you, how big is an electron, what are you talking about? The size? If it's the size, then you can't answer it, right? Or you can say it's 0. Right? But if somebody asks you, what is the size of a proton, can that be answered? Yes or no? Yes. How come the proton's size or dimension can be determined, but the electron can't? Well, these are just, observations so far. We got to think about the theory that underlies that, because the theory that underlies this kind of stuff will give us a more clear, fundamental picture of what's happening. Okay. But anyway, yeah, these protons are very small. Are they round? Protons round? Spherical? Are neutrons round and spherical? No. What's going on inside that nucleus? Well, I told you that chemists, the most important electrical force in chemistry is, actually, no, I got it mixed up. The most important force in chemistry is electrical, right? Do chemists care about nuclear forces? No. Chemists don't care about nuclear force. So chemists, they don't really care what's inside that nucleus. They just know the charge on the nucleus. What they do care about is the total charge on the nucleus. So the charge on the nucleus consists of the protons, the positive protons, and the neutral neutrons. And so we want to know the charge on that, because the charge on the nucleus is what holds the electrons in the atom. But the actual structure of the nucleus, you know who cares about the structure of the nucleus? Nuclear chemists care about the structure of the nucleus. Chemists, they don't care because nothing happens to the nucleus in a chemical reaction. The atoms stay the atoms, they just get rearranged, right? Except for one thing. We have to care about one thing about the nucleus. And I'll talk about that in a minute. And so here, who determined the mass? How is the mass of a proton determined? You don't have to know. Who discovered the proton? You don't have to know. You should know the mass. You should know the mass of the proton to how many sig figs? You should know it to 2 sig figs. To 2 sig figs, it's easy to remember. The mass of a proton is 1.0 U. But to more sig figs, then you can look that up. I think it's 1.00733 U. We'll look it up. You should have it memorized, but it's known to more digits. It's 1.00 to 5 sig figs. It's 1.0073 U. The charge on the proton. What is the charge on the proton? Positive 1. The mass on the neutron is, to 2 sig figs, what is the mass on a neutron? To 2 sig figs. 1.0 U. So to 2 sig figs, the proton and the neutron have the same mass. But, you know, they don't weigh the same. You know, we need more sig figs to see that they don't weigh the same. The neutron's slightly heavier at 1.0087 U. You don't have to memorize these. But the proton's slightly lighter, the neutron's slightly heavier. Both of them have a mass of about 1 U. The electron's mass is much smaller. The electron's mass, most people remember to 1 sig fig, 0005. 0005 U. But the electron's mass is known to 5 sig figs here as well, and actually probably more than that. 0005, 4, 858. There's something that's funny that happens with mass. For example, let's say I wanted to weigh out some protons. You probably can't do this, right? You can't weigh out protons, but let's say you try to weigh out protons. I try to weigh out protons. I want to weigh out, you know what? I want 2.0000 U's worth of protons. Is it possible to get 2.0000 U's worth of protons? Can, you know, if somebody could get 2 protons, how much would that weigh? 2 protons should weigh double this, right? And then I don't want that much. I don't want 2.014. I want 2.000. Is it possible to get that mass? It's impossible to get that mass of protons. Why? Because the problem is I can't shave a little bit of one, you know, I want 2 protons and then just slightly less. And so can I get 2 protons and then shave a little bit of the second proton's mass off? No, that's impossible. And so that's what's called a forbidden mass. Is that kind of weird? Usually when you think about mass, you should be able to weigh out any amount you want. If you want, you know, 1.1 kilograms, no big deal. 2.0 kilograms, no big deal, right? Are there any forbidden masses? Like if you go to buy some, what do you buy by mass? Yeah. Well, you know, when you go to the store to buy something, you know, are there any forbidden masses? No, you just weigh out the amount that you need, right? Normally, that's the way we think. We think in a continuous world. But when we get to these very fine, small particles, then we don't live in a continuous world. We live in what's called a quantized world. In the quantized world, there's forbidden masses. So, for example, a mass of 2.0000 U's worth of proton is forbidden. Why? Because we can only have integer multiples of this. We can have 1 proton, we can have 2 protons, we can have 3 protons, but we can't have part of a proton. Does that make sense? And so this is like if you're going to a gravel pit and you're weighing out the sand. The sand costs what? X dollars per pound or something like that. You can go fill a sandbox with it. But you know, when you're thinking about sand, well, you could buy any number of pounds you want, right? But that's not really the case. Sand is quantized too. How is sand quantized? Let's say I have sand, but now I want to add a quarter grain of sand more. Not a whole grain, just a quarter grain. Well, I guess you could take a hammer and crush it. But let's say you didn't have a hammer. Well, the salesperson says, no, sorry, you can't get a quarter grain more. You have to buy full grain more because you got to buy it according to an integer number of grains. or crystals of sand. Does that make sense? Well, the same thing here. This is quantized. But we don't really think about that much. Where we think about it is the charge. This is not the actual charge. This is what we call a quantum number, or fundamental unit of charge. The actual charge on the electron is not -1. Do you know what the actual charge on the electron is? -1.6 022 times 10 to the minus 19 coulombs. -1.6022 times 10 to the minus 19 coulombs of charge. And so let's say I don't want -1.6, I want -2.0. Is -2.0 an allowed unit of charge for the electron or a forbidden unit of charge for the electron? Can I have -2.0 times 10 to the minus 19 coulombs worth of charge? No, it's forbidden. Why is it forbidden? Because the next allowed unit of charge would be -3.2 times 10 to the 19. So I'm allowed 1.6, I'm allowed 3.2, I'm allowed, what's the next one? 4.8. Next one, 6.4. But everything between these is forbidden for the electron. This is called quantization, and we use quantum numbers to express this. So the quantum number is we call n. And so what do we allow? The allowed charges for electrons, or a group of electrons, is n times the fundamental unit of charge, which is 1.60 times 10 to the minus 19 coulombs. And so rather than representing the charge using this, we'll represent the charge using n. And so this is plus n here. This charge is minus n here, because the next allowed one would be -2, which represents 2 electrons, where n is equal to -2. This is -3, -4. And so these are called quantum numbers here. And we see this when we start working with very minute quantities where things, jump up because we got to buy them per piece. It's not a continuum. Normally when we're thinking about things, we think in terms of continuous. Any charge, like 2.0, 2.1, 2.3, whatever we want, right, is available. Okay, so normally we represent the electron's charge using these quantum numbers. -1 charge for 1 electron, -2, etc. +1, +2. But when we think about these, this actually refers to this, as you probably are already aware of. All right, now we know what the atoms are made up of, and so the composition of an atom is given by its nuclear symbol. And so we have the symbol for the element, and we have 2 numbers or letters that designate the composition. The first one, A, this is called the mass number. The mass number does not equal mass. What does the mass number equal? Well, I shouldn't say it doesn't equal. It's close to the mass, but not exactly the mass. Just close to the mass. The mass number actually equals the number of protons plus the number of neutrons. So it's a number, not a mass. But since electrons don't weigh much, this is close to the actual mass of an atom, because electrons are about 2,000 or 1,850 times lighter than a proton or a neutron. Z, this is called the atomic number. And the atomic number is the number of protons. The atomic number, this is optional. Why is this optional? It's optional because, what defines an element are its electrical characteristics. And so when we look at the nucleus and we see how many protons, 9 protons will behave differently than 10 protons, which behaves differently than 11 protons, chemically. And so the chemical properties are going to be subject to that charge. So Basically, the atomic number just tells us what element we're dealing with. Element number 9 has 9 protons. 9 protons is going to behave like this because we're interested in electrical interactions. And so Z is often not written. Chemists are mainly interested in electrical properties, except for one thing. There's only one nuclear thing that we should talk about now, and that's something called the mass defect. We'll do an example of the mass defect. Fluorine-19. This isotope of fluorine, I know its composition. What is this atom of fluorine made up of? This atom of fluorine has, I'll look on the periodic table, it has an atomic number, or it's element number 9. So element number 9 has 9 protons. If it has 9 protons and it's neutral, then the protons must balance out the electrons, so it has 9 electrons. It's not an ion. And if we look at Z plus the number of neutrons is A. And so the number of neutrons must be 10 neutrons. And so here's the composition of fluorine-19. But wait a minute, is that really it? Isn't there more in atoms than just protons, neutrons, and electrons? What about quarks or bosons or that type of stuff? Shouldn't I add those to the list or not? Should I add quarks and bosons? Whatever else? Yes? No. Because, you know, nuclear chemists, they're interested, well, what is a proton made out of? Well, chemists will say a proton's made out of a proton, but nuclear chemists won't say a proton's made out of a proton. It's got to be made out of something, right? Giving its properties of the proton. And so nuclear chemists are trying to decompose protons to see what protons are made out of. And break these up into smaller pieces so that they can figure out why they behave the way they behave. What's the structure, what's the property, what's the composition of these. But for chemists, we just focus on these. We aren't going to break these apart because the nucleus, again, is not changed in undergoing chemical reactions. And so one of the simplest things we can do right now is we can determine the mass of a fluorine-19 atom. Well, the easiest way to determine the mass of a fluorine-19 atom is just do this. We got 9 protons, and so that's going to yield 9 times the mass of a proton, 1.0073 U. And so if we got 9 of those, it's going to be 9 times that, which is 9 point what? Can somebody punch this out in their calculator? Zero, 6, 5, 7. Give me one more digit. That's it. Okay. Yeah. So we got 5 sig figs. How many sig figs is 9? Infinite or 1? Infinite. It'd be infinite because if this were 1 sig fig, then the precision there would be between 8.5 protons and 9.4 protons. Can we have a half a proton? No, it's quantized. It's going to come in units of integer units of protons in that sense. Okay, when I talk about quantum mechanics, I'm not talking about this, the whole quantum physics stuff. It's going to be thought of a little bit differently, so I'm just introducing some of the conceptual stuff right now. Okay, we have 9 electrons. It's going to be 0.00054858 U. And so can somebody calculate that?
One zero zero 4937.
4937. 22. Okay, we're allowed 5 sig figs, so I'll go 49372 U. I should align these better. 10 neutrons, we got 10 times 1.0087 U. So this should give us 10.087 U. And then we just add up. And so we know what the atom's made of. We just combine the masses to figure out the mass of a fluorine-19 with some. When we do an addition, do we care about the sig figs or do we care about the decimal places? Yeah, the decimal places, so let's see. We have 4 decimal places here. I didn't draw this so great. So we'll go out 4 here. And, oh, we only have 3 decimal places, sorry. 3 decimal places. So I'll go out 3 here, 3 here, and 3 here. And then add it up. And so these aren't significant, but we'll just go ahead and add it. 2, 7, 3, 9 and 7, 16. And then bring the 1 up. 5 and 5 is 10. That gives me 17. 6, 7, and 8 is 15. Gives me 1. 19.157 U. Okay, does that look okay? Now, the thing is, sometimes when we do this kind of stuff, the precision doesn't quite work out looking at the sig figs. Because let's look at our original data. What was the precision in our original data as far as mass goes? And so here, the precision was about plus or minus .0005. In other words, plus or minus 0.00005, half of that last digit. What was the precision here? The precision here was a lot of zeros and a 5. Very high precision. Here, the precision here was .0005. And so it looks like in our original measurements, the uncertainty was about .0005, .0005. But when we look at this, it looks like it's not .0005, it's just 0005. And so here's a case where, sig figs might have failed because maybe more accurate representation of the uncertainty would be a .0005 in this mass. But we'll see later how we deal with this when we add these here. It could bump up to there. We'll talk about it later. But anyway, this is the mass. Is there a way to weigh atoms? We just calculated the mass. So can we weigh, let's say you wanted to weigh a single atom. Is that possible? No. Even if you use the STM, you have used the STEM probes, these very tiny probes. They're so sharp at the end, like atomic dimensions. I guess you could get 2 STEMs and then pick up an atom like a chopsticks, something like that, and then place it on a balance. Is that possible? No. Is there any balance that can weigh a single atom? And therefore, it must be impossible to weigh single atoms. True or false? Impossible to weigh single atoms. True or false? It's true if you try to weigh them on a balance, but is the balance the only way we can weigh? No, it turns out we can weigh other ways too. And it turns out it's true, we can weigh single atoms. How do we weigh single atoms? Well, we have a special instrument that can do that, and it's called a mass spectrometer. In the mass spectrometer, what it does is it shoots a stream of atoms here. And the atoms are neutral, so they aren't going to be influenced. This is a magnet here. They aren't going to be influenced by magnetic field. But what you do is you charge them. You either shoot a beam of electrons, i.e. cathode ray, or you shoot something else at these atoms as they pass by. And so either they pick up an electron, an electron gun or cathode ray, or you knock an electron off it. And so when you create a charged atom, then it can be deflected. And so what they do is they charge the atom, so you get a stream of positive ions. So they must have knocked an electron off. And these get deflected in the magnetic field. And the angle of deflection depends on their mass. And so the light ones are highly deflected, whereas the heavy ones aren't. And so based on the mass spectrometer, the angle of deflection, we can determine the mass. But we need to first calibrate our mass spectrometer. And the mass spectrometer, this usually measures in U, atomic mass units. And so what I need to do is I need to feed in here a 1U standard. Locked away in some vault in Washington, D.C., is there a 1U standard? I know there's a 1 kilogram standard, so they got to have a 1U standard too, right? And then I get that 1U standard and I feed it in here and see where it lands, and then I know, hey, this is exactly 1U, or as close as I'm going to get. It's like that kilogram block. If you had that kilogram block and you had access to it, you can calibrate your balance and it'd be just right on, or as close to right on as you're going to get. Right? It's probably not perfect, but as close as you're going to get. And so what weighs exactly 1U? Do they have a chunk of metal stored out there that weighs exactly 1U? No, you know what? Maybe they just take a proton and shave a little bit. All they got to do is take a proton and shave off 0.008, or no, 0.0073 U's worth of mass, right? Is that possible? No, and so what in the heck weighs 1.0 U? 1.0000, as many zeros as we can get, U. You tell me what we're going to use as a 1U standard. I'm sorry. Yeah, okay. Carbon 12? It's related to it? Yeah, you're absolutely right. There's no such thing as a 1U. Nothing weighs 1U, right? Nothing. If a proton was 1.0073, a neutron weighs even 10, 20 electrons, 200 electrons, 2,000 electrons. Would 2,000 electrons weigh? No. That's a forbidden mass. 1.00 U is a forbidden mass. There's nothing. And so how the heck is a U defined? It's based on carbon 12. And it's not a U that defines it, it's 12U. And so the definition of the U is this. An atom of carbon 12 is defined to weigh exactly 12U. And so now we can calibrate this easily. Because what we do is we got to vaporize the carbon 12 atoms. We introduce the carbon 12 atoms in here, ionize them. And wherever the carbon 12 atoms land, we set the spectrometer to read exactly 12U. And then that's our standard, so everything else is weighed relative to our standard. So if it's lighter than that, it'll hit over here. If it's heavier than that, it'll hit over here. And using some physics, we could figure out the mass of single atoms. And so we could weigh single atoms like this. And in fact, that's exactly what's done. And you can find these masses in books and tables. The masses in books and tables are from calculation like this. Necessarily. I guess they could be, but they aren't because something weird happens. So we're going to weigh fluorine-19 in a mass spectrometer. When we weigh fluorine-19 in a mass spectrometer, then the mass comes out to 18.99 8403. Okay, so when we weigh it in the mass spectrometer, it comes out to 18.998403. When we calculate the mass, it comes out to 19.157632. So what's going on here? Would you attribute this error to experimental error? You know, people love that. You know, oh, there's an error. Well, it's experimental error. There's an error because these two masses should be the same, right? It's the same thing. And so, can we attribute this to experimental error? No. I mean, this is way too precise. It could be due to a systematic error. But no. Many people have calibrated this very carefully. Many people have gotten this same number repeatedly using different mass spectrometers in different parts of the world. And so they keep getting this number in the mass spectrometer, and we keep getting this number by calculations. So which one of these is wrong? Is the calculation wrong? These masses are also reproducible. Is the calculation wrong? You know, maybe we're missing something. No, we aren't missing anything. We have everything. In fact, this looks like we have too much of something, which we don't. Or is the mass spectrometer wrong? Which one is it? Well, the thing is, whatever our theory is, you know, this atom that consists of protons, electrons, and neutrons, whatever our theory is, our theory has to match experiment. If our theory doesn't give us a fundamental explanation of the facts, this is factual. You know, once it's been reproduced this many times, this is factual. And so if our theory does not match our facts, we got to either modify our theory or abandon it. And so maybe it's time to rethink our theory? No. And this is called the mass defect. There is a mass defect because the masses aren't matching. And this is why you need a little bit of nuclear chem in chemistry. You need a little bit of nuclear chem in chemistry because of the mass defect. The mass defect is a result of this. You know, the combined mass, that is 19.1576, or you can carry that, U. This is the total mass of particles. Is equal to the mass of the atom, 18.998403 U. This is the mass of the atom plus the mass defect. And so some of the mass is missing, and that mass we call the mass defect. So what happened to this lost mass? Let's talk about that. Okay, in the mass defect, some of the mass of the nucleus was converted into the nuclear binding energy. We can figure out how much nuclear binding energy we generate. Delta E is called the nuclear binding energy. This is equal to the mass defect, delta M, times c squared. C is the speed of light squared. So this is E equals mc squared, which talks about this nuclear force. We need the nuclear force because that's what holds the protons. You're cramming 9 protons in the space of the nucleus, which is incredibly small. So no nuclear force required to hold the protons together. And so we know that the electrons don't scatter out everywhere. What holds the electrons in an atom? The electrons aren't going to fly and repel each other, right? If they're all repelling each other, they're going to get as far away from each other as possible. The electrons are confined to the atom because they're being held to the atom by protons. Protons, and that force is called an electrical force. But why don't the 9 protons in the nucleus repel each other and scatter out? What's holding the protons inside the nucleus? I know what's holding the electrons in the atom, but what's holding the protons in the nucleus? What's holding it is called the nuclear binding energy. You know, and we want a fundamental picture. We want to see what's actually going on, you know, but it's not so easy, you know, because there you have the nuclear physicists trying to figure it out. You know, they say the neutrons are like some glue holding the protons together, et cetera, et cetera. Could be shells inside the nucleus. So the theory of the nucleus is where you'd go to get a better picture of what's happening in the nucleus, but we aren't going there. The only thing we're going is we know that there's going to be a mass defect. And so what this says is this. It's impossible to calculate the mass of an atom, you know. And the reason it's impossible is because the mass defect changes, you know, depending on how strongly bound that nucleus is. Some nuclei are exceptionally strong and stable. Other nuclei are exceptionally weak and unstable. Those nuclei that are exceptionally weak and unstable, we call those radioactive because the nuclei are going to fall apart. And they often end up breaking into pieces. Okay, so we have to use the mass spectrometer to weigh atoms. Well, talking about unstable nuclei, I just want to talk about one more experiment here for this. Do you recognize this? Do you know what these are supposed to represent? These are supposed to represent little chunks of the nucleus. You know, there's some radioactive atom source over here, and this radioactive atom source decays and little chunks of the nucleus break off. These little chunks of nuclei are called alpha particles, and the alpha particles actually have a +2 charge, but they just want to show the rough charge here. Because alpha particles consist of 2 protons and 2 neutrons, and so a little piece of the nucleus breaks off. And these alpha particles, Rutherford used to shoot at a piece of metal foil, gold foil, the Rutherford gold foil experiment. And so what was the end conclusion or an end result of the Rutherford gold foil experiment? The Rutherford gold foil experiment was used to determine or distinguish or differentiate 2 models of the atom. One model of the atom was called the plum pudding model, in which everything was kind of dispersed in the pudding. Another was called the nuclear atom model. And the Rutherford experiment determined which of these models to be correct. The nuclear atom, because some of the alpha particles hit the nucleus. Why would an alpha particle bounce off the nucleus? Why wouldn't it just kind of stick in there, get absorbed? Because the huge electrical repulsions. And this one gets close to the electrical repulsions strong, but as you get farther away, the electrical repulsions decrease dramatically because it's based on the square of the distance in the denominator. And so it drops off rapidly. So these are pretty much not deflected at all. And so it depends on how close you get to this positive charge. Well, let's go back to the mass spectrometer. And we're going to talk about the mass spectrometer next after the break. So let's take another break, 10 minutes or so, and start again.